So I'll step into a composite beam example now. Step one is to determine the centroid of the cross-section when I have multiple materials. If I have I materials, then I'm going to have to do this calculation where A is the area of the cross-section corresponding to material I. Y bar I is the centroid location of the cross-section of the material that corresponds to material I relative to the top surface of the full cross-section. And AI, again, is the area of the cross-section of material corresponding to I material. And NI was given by this ratio. So the modulus of the ith material divided by E1. We're going to reference everything to one material. We'll determine for the inertia of the entire beam by using this formula. And these are the moments of inertia. And that's the moment of inertia for part one or portion one of the beam. We'll then determine the maximum moment of the beam. And then we'll calculate the maximum stress at the furthest point away from the neutral axis. In this case, you'll just use this formula and then figure out where the neutral axis is, and the furthest point will have the highest stress from that point away. So that was step by step, but let's apply that to a problem. In this case, it is given to us that the beam is subjected to a bending moment of 20 kilonewtons per meter around the horizontal axis, around the z-axis. And what we have here is the modulus of a wood material that's 100 millimeters wide, and we're talking about this piece here, and 200 millimeters deep. We also then have aluminum plate at the very bottom, which has a modulus of 70 gigapascals. So very two disparate modulus, and it has a section that's 80 by 20. They want to tell us where they want to ask us, where's the highest stress for each of these materials? And so we're going to go ahead and do that. We'll transform the section to figure that out. So given this information, the modulus of the two different materials, we want to determine the maximum stress. We'll do it for one of the sections. We'll do it for wood. I'll let you do it for aluminum. But at the end, you should get the same answer. So I'll use the wood as a reference material. I want you to try with aluminum as a reference material, but the reference material always goes at the bottom, and that corresponds to this wood material. So what is the area of the wood material? It's 220 times 100. You can see that there. And where's the centroid of this piece from the top surface? That's 110 from there. You can see that because this 220, that's 110, this point here. And can be easily calculated. We were given 70 divided by 8.75 will give exactly 8. So that's what goes there is the 8. Now, what is the area of this aluminum cross section? That's 80 times 20. And so 80 times 8 is 640. And that 20 is this one here. And then the centroid of this piece can be found. So it's 220 plus half of this is 230. So 220 plus half of 20 is 230. That's what you see there. The area for the wood section here is 100 times 220. And then I have the area times n. N is 8 times 20. So 8 times this width 80 is 640 times 20. is its height. So that's what you get by multiplying that. So y bar is 154.1. And so that's from the top cross section, you know exactly where the neutral axis is. The moment of area measured from the neutral axis can now be calculated. So we'll have to do that for, so if you recall, we have to do this calculation here. So that calculation requires calculating the moment of inertia of this of the wood piece, of the aluminum piece separately, and then we have to use the parallel axis theorem to determine the distance between the centroid of this piece to the neutral axis location. So let's do that. IW is 1/12 the width times the height cubed. I did that here. 100 times the height cubed, 220 cubed, plus the area, 220 times 100. You can see that there. And then I have to multiply that by the distance between the centroid of the wood section and the neutral axis. So the centroid is a 110 of this wood material, while the neutral axis was a 154. So 110 minus 154 is 44.1, and that's squared. I'll then repeat that for the aluminum piece. That's 1/12. The width is 80. The height is 20. And if you notice here, the formula has an n here of 8. So 8 times 80 is 640. Okay, so I just included it there. 20 cubed is the height. 20 is the height. 20 cubed is that calculation. Plus the area of this term here. 80 times 20. Again, 80 times 8 is 640 times the height is 20. And then the distance of that point relative to the neutral axis, we have to go from the very top to the very bottom. That's 110. 220 times 10 is the location of that point, is 230. 230 minus 154, which is where the neutral axis is, will give us the distance between the neutral axis location and the centroid of this piece, 75.9. I add the whole thing up and I get the moment of inertia of this composite cross section. I can now calculate the stresses MC over this effective moment of inertia. I did it here. And for the aluminum piece, I have to put an N there, and I can use the same formula. The maximum stress for the wood, you can see that's a neutral axis. So then we want to use this distance then, because that's furthest away from the neutral axis. So that's 0.1541. I recommend that you try checking it. The moment was given to us as 20 times 10 to the 3. If you don't recall that, I'll remind you. 20. And IT was calculated here and here. So that's that, 14.8 megapascals. For the aluminum piece, which is this piece right here, I find that I have an N of 8, M is given, and I have IT. How do I calculate this C? So we're looking at this piece here now. So from this point, the point farthest away is over here. So now I'm able to then find the stress which occurs in the outer fiber here. For 100 points extra credit if you're able to use the bottom material as a reference axis, as a reference material. So I use the wood as a reference material and aluminum as the one that I'm using to refer to the wood material. But if you try the same analysis by using aluminum as a reference material now, which means EA goes in the denominator, and you get the same answer and you show it to me and you show it to us, we'll provide you the extra credit. Here's a good example problem that I recommend that you try. And we'll be going over this later on. With that, this concludes this recording, and I appreciate your time.